on that. But anyway, I took the weekend completely off. So if I haven't gotten back to you any of your emails, and I see there's a lot of them, a lot of people have emailed me on Friday about attendance, or you had questions about labs, or you've turned in labs. So just want to let you know, I haven't checked any emails, so it's not that your email's missing. I just haven't gotten to it. What else to let you know? Lab 3 will be due Friday at midnight, and I'm just putting some finishing touches on it, and I'm going to post it to Google Classroom today. So you should have access to it by today. And then, like I said, it'll be due by Friday at midnight. It's completely online. There's videos embedded in the worksheet. Like, you click a link and it takes you to a video of me explaining the lab. So because of that, we will not be meeting online or in person at Wednesday or Friday from noon to 1:50 like we usually do. So any questions about that? We're just not meeting for lab at all this week because it's all online. That being said, when you're doing the lab, if you have questions and if you need help from me, we could just let me know, email me, either meet me online for office hours, or we can figure out a different time to meet online and I can walk you through it. So I'm here if you need me, but you probably will not need me. So that's it for the lab. The last thing to tell you, I think, the last announcement is the exam. So we need to know if we're going to take the exam on Wednesday or on Friday, and that's up to you. So you guys email me, even though you in person. If you have an opinion, email me and let me know. Regardless of if we take it on Wednesday or Friday, it's only going to cover the first 3 chapters, right? The stuff we have already finished. That's the only thing it's going to be. It's going to be about 50 questions, and it will be online. So taking it Wednesday or Friday doesn't change anything about the exam itself. It's just which day it's on. So like I said, email me, let me know. There are study guides on the Google Classroom. And like I said, I haven't checked all my emails, but it looks like a lot of people have not done the study guides. Obviously, you don't have to. It's independent work, so it's optional. But I would highly recommend it, because when I write the exam, I'm going to take those questions and I'm going to reword them. So you have access to the questions that are going to be on your exam. So now it's up to you to do them. So any questions about any of those things? All right, so we can just jump into it then. We are skipping chapter 4. So we are going directly to chapter 5. Let's get this to work. Oops. Okay, so if you are online, you should be seeing my PowerPoint screen right now. If not, someone let me know, but let's just move forward. Oh, that's old. It's obviously not 2019. Kind of wish it was. Be better times. But anyway, yeah, we're doing chapter 5, that's called the working cell. I don't know, to me that's slightly inaccurate, or there'd be a better name. To me, I think the better name for this chapter would be energy. This is all about energy. And yes, it's about energy in the context of cells, but still, it's all about energy. This whole next section that we're going to cover is all about energy. So your exam, your next one, exam 2, is going to be all about energy. So the reason we skip chapter 4 is because chapter 4 is basically a tour of the cell. It tells you what all the different parts do. And the reason we skip that is because you're going to learn all the important parts of the cell when you learn what they do. Like in this chapter, you're going to learn about diffusion. So you're going to learn about the cell membrane. You'll learn about chloroplasts when we talk about photosynthesis. You'll learn about the mitochondria when we talk about respiration. So that's why we're skipping chapter 4. I highly recommend reading it. It definitely won't hurt you, but I'm not going to ask anything about it on the exam, because again, you're going to learn the most important parts of the cell as we move forward. So there's no questions about why we skip chapter 5 or chapter 4. Let's jump into it. Let's try to jump into it. Work the other. Oh yeah, there we go. So anybody want to play the guessing game? We'll do this. Why not? We're ahead of schedule a little bit, or right on schedule. Any idea why your book might have somebody in a hazmat suit? And remember, this is published before COVID, so it has nothing to do with that. Any guesses for those of you?
Biological.
I like that. So you mean like a biological hazard type thing?
Yes.
That would be a good guess, and that would be relevant to this chapter. But your book is actually, if I remember correctly, they're hinting at something about nerve gas. Like that person was apparently protecting themselves from nerve gas. And in this chapter, by the end of this chapter, you'll understand how nerve gas works, sort of. That's not the purpose of this chapter, but you will know a little bit about it. How about this picture of raisins? Does anybody know, or these raisins and this beef jerky? Any idea what they have to do? Yeah, dehydration. That's good, because you're going to learn the process. It's not necessarily of dehydration. We're not going to teach it that way. But the process that does that is you've got things like osmosis, and you're going to learn about that in this chapter. How about this pizza and these people going for a walk? What might that have to do with each other in this chapter about energy?
Burning calories.
Good. Exactly. So yeah, the pizza is all about the calories coming in, and then the taking the walk is all about burning the calories. Which, by the way, is a great idea for independent work. If you want to, you can look up your favorite foods, like how many calories are in my favorite foods, and then also maybe look up some of your favorite activities and how many calories that burns. Even if you just like sitting on the couch, technically you are still burning calories. So look that up if you want. Any questions about the guessing game stuff? As always, that will never be on the exam. I'm just trying to do the introduction. All right. Sorry, I'm making a slight adjustment to my screen here. All right. As always, the beginning of your chapter starts with this biology and society. Again, the textbooks authors are trying to get you interested in this in the chapter and say, this is why this is relevant to your everyday life. So as always, or almost always, I'm going to skip this because I'm not going to test you on it. You can read about it if you want, and if you have questions, you can just let me know. Yeah, we'll skip all that. Basically, this little introduction uses words like enzymes and sugar, right? Things like that, and your textbook authors want you to be like, what's an enzyme? And that's exactly what we're going to find out. So anyway, let's jump into it. Before we can talk about how cells use energy and why they need energy, we're just going to have some basic energy concepts. Hopefully this is going to be a review for a lot of you. So first thing you need to know, and I guess I'll probably have this on the exam. Does anybody know what the definition of energy is? That's like one of those words where everyone knows what it means. It's just that when you're sitting in class and someone asks you to actually define it, sometimes you draw a blank. Energy is the capacity to cause change. So if you're taking notes, write that down or highlight it or something. That is important. That will be on the exam. Energy is the capacity to cause change. Your book points out that some forms of energy are used to perform work. And some examples of that is moving an object against an opposing force. Like this picture here, that guy trying to push a boulder up a mountain, right? So in that case, the opposing force will be friction and a lot of gravity. One thing I usually see people get confused with on the multiple choice exam is that they will choose the wrong option for what is energy, and they will very often put energy is the capacity to perform work. And that's not true, right? That's too specific. Yes, you can perform work with energy, but that's too specific. You have to be broader. It is the capacity to cause change. And think about not just change, right? So not just work, not just pushing something against an opposing force. What if I take the thermostat and lower the temperature, right? That's causing change. That's going to cause a change in the temperature in the room, which takes energy. Is there any questions about the definition of energy? All right. There's two different types of energy. Does anybody know the two basic types of energy? You've probably heard this before. No guesses? Yep, somebody here said it. Kinetic is one of them. And the other one is potential. So kinetic energy is the energy of motion. Potential energy is stored energy, basically. And if you're taking notes, you write that down. That will definitely be on the exam. You definitely need to know the differences between kinetic energy and potential energy. Now, a lot of times when people teach about potential energy, they really only focus on the stored energy that something has due to its location, because you'll see that a lot. Like, it's easy to demonstrate. If I've got these two identical dry erase markers, I've got one up here and one down here. Which one has more potential energy? The one up high or the one lower? You guys are going to put me to sleep. The one up high has more potential energy, right? It has more stored energy because it's higher. So that's usually the demonstration you see when people talk about stored energy. But it's more than that. It's also energy that's stored because of the structure. And that's less intuitive, but it's more important, because that's the most of the energy that we're talking about, is energy that's stored in structure. And what I mean by that is, take, for example, a bow and arrow or a crossbow. You know, when you pull it back, however much energy it took you to pull it back is ready to be released when you let go of it, right? So that is energy stored in the structure of that object. And we're going to talk about that a lot in this next 3 chapters. It's all about the energy that's stored in the bonds, the molecular bonds that we'll talk about later. Does anybody have any questions about the difference between kinetic energy and potential energy? All right. You should also know this: the conservation of energy, which states that energy cannot be created or destroyed. It can only be converted from one form to another. So as we understand the universe, all the energy that's ever been is still there. It doesn't go away. There's never any new energy created. It's just converted from one form to another. So like the energy stored in the chemical bonds of coal, when you burn the coal, you release that energy, that chemical energy, that then turns into heat energy, right? That heats up some water, which causes steam, and then the steam turns a turbine, so then it's converted to mechanical energy, and then we take that turning turbine and convert that to electricity, right? So it's, again, converted from one form to another. And if you live in this area of West Virginia, then that electricity is now going through your computer as you're watching this, or you have your computer, but the one person doesn't have a computer right now. But yeah, so again, energy just gets converted from one form to another, and life depends on this conversion of energy. Without that, there just wouldn't be any life. And remember, that is also one of the properties of life that we learned in chapter 1, right? We have to convert energy from one form to another. So any questions about this slide before we move forward? The next slide is just a picture that kind of demonstrates what we're talking about, going from one form to another. You can see this person up here. They have their greatest potential energy when they're up there. And then when they jump, that energy is being converted, right? Until finally, it's because they have kinetic energy, because they're moving. And then they hit the water, and they have the least potential energy that they're going to have in this cycle. Now, when they hit the water, right, they have kinetic energy, but what happens? You think, you've seen people jump into the water. What happens when they jump into the water? Yeah, there's a splash, right? You can see it, you can hear it, and that's energy being converted. That's your kinetic energy being converted to, well, different types of kinetic energy, because when you hear it, that's air, right? That's the vibration of the air. So again, energy is just being converted from one form to another. Does anybody have any questions about this slide?
Oh.
All right. If you download the PowerPoint, you can watch this little video. It's basically an animated animation of what I just talked about. So let's talk about heat. We already have a little bit unofficially. We discussed this, I think it was last week. I was giving you some information about it. But here we go. You need to know this for the exam too. Heat is a type of kinetic energy, and it is the random motion of matter. So as stuff moves, as stuff moves, right, which is kinetic energy, as it moves, that's what heat really is. So when you say it's hot in this room or cold in this room, you're really describing the movement of the air molecules in that situation. Right? If I'm saying it's hot, that means those air molecules are moving around a lot. If I say, oh, it feels cool today, which it does, I like it, we would say the molecules are moving around not as fast as they were. That's the most important thing, I think. That first bullet point, heat is a type of kinetic energy. It's a random motion of matter. That's the most important part. Also, Yeah, it is the most chaotic and disordered form of energy. That's not terribly important. You don't necessarily need to remember that. And also, all energy conversions generate some heat. That's a little bit more important than the middle one. But yeah, so as we go from one form to another, things get hot, right? That's why, if you have your phone plugged in, it might warm up as it's charging because you're going from AC power to DC power. You're converting it from one form to another. And that brings us to entropy. And entropy is really, really important if you're doing things like chemistry and you're actually accounting for energy mathematically. So if you're using math to account for energy conversions, entropy is very important because it helps you basically account for energy. But in this case, in my opinion, I don't think it's that important. If for some reason after I teach you this thing about entropy, you just completely brain dump it and forget what I said, I think you'll still be fine for the rest of the semester. As far as I'm concerned, entropy, it's not important in the context of this 100 level biology class. But it's in your book, so we'll talk about it quickly. Entropy is the measure of disorder or randomness in a system. And every time energy is converted from one form to another, entropy increases. So that's what entropy is. And again, in the context of this class, it's not very important. Oh yeah, sorry. Does anybody have any questions about heat or entropy? Okay. Here, this is a little bit more important in my opinion. Chemical energy, because everything we're going to talk about in the next 3 chapters, this is what it's all about, the chemical energy. And I kind of hinted at this earlier, but now we're actually going to talk about it. Molecules have a form of potential energy called chemical energy. So you need to know that chemical energy is a type of potential energy. You might be wondering what this picture has anything to do with what we're talking about. Any idea what this picture, like, it's because it's not in your textbook. Any idea what I'm trying to get at with this? Yeah. Exactly. For those of you online, Carson was saying that these are 2 magnets with a like side, so they repel each other, right? So these people are pushing really hard trying to get those things together, but they won't, right? They'll repel each other. And I'm sure you've done it before. I'm sure you've pushed magnets together. You can do it, right? It just takes energy because they repel each other. That's what I'm getting at with chemical energy. Because what's on the outside of an atom? Do you guys remember? You need to know that for the exam anyway. So between protons, electrons, and neutrons, which ones would you find on the outside of an atom?
Electrons.
Good, electrons. Hopefully you guys are just too shy to answer and you know the answer. That's really basic and really important. But yeah, it's electrons. So if you take 2 atoms and you want to put them together, they're going to, this is very basic, all right? If you look into this, what I'm going to tell you isn't exactly true, and it all depends on a lot of different things. But it's a good way to visualize this, and that'll help. So bear with me. They're negative, right? Electrons are negative. So if you try to put 2 negative things together, then they repel each other, right? So however much energy it took to squish those atoms together to make a molecule, to make that chemical bond, however much energy it took, that's how much energy will be released when you break that bond. And that's a very important concept for what we're going to talk about for the next 3 chapters. So just remember that in the back of your head. However much energy it takes to build a molecule, that's how much energy will be released when you break that molecule. And each molecule is different. We'll talk about some different molecules later, but some of them are a lot easier to build. And they take a lot less energy to put together. Some of them take a lot more energy. But anyway, that's what I was getting at with that, right? So things repel each other. It takes energy to put them together. However much energy it took to put them together is how much energy will be released. Same with the crossbow, like I said earlier. However much energy it took to pull that thing back, that energy is there. It's stored, ready to be released when you pull the trigger. And in a way, that's like a molecule, right? That is the chemical bond. That is the chemical energy. So are there any questions about chemical energy? I mean, we'll talk more about it, but are there any questions so far? All right. Move forward then. I like that your book draws this comparison. Cells and engines, like engines in your vehicles, they use the same basic process to make chemical energy that are stored in fuels available for work. So your cells and your car, if you have one, at the molecular level, they're almost doing the same thing. They break fuel, these big fuel molecules, They break them down into smaller waste molecules, and with that, there's much less chemical energy than there was to begin with, right? So you have these big molecules that had energy. You break them down. Now you have smaller molecules. They have less energy. And as you do that, like I said, when you break a bond, you're releasing energy. So in the case of a vehicle, that energy is used to push your car or make your car move, right? And in the case of cells, you don't need to write this down yet because we're going to talk a lot about it later. In the case of cells, we use that release of energy to make something called ATP. And we'll come back to that later. But you can see here, again, it's very similar because you're doing it both in the presence of oxygen. You're basically burning it, right, in the presence of oxygen. And then the byproducts are carbon dioxide and water for both your vehicle and you. So any questions about that? That certainly won't be a test question. You don't need to know anything about octane and gasoline, right? That's your book just did a good job of making that comparison because everybody's familiar with using gasoline to make your vehicle move. So let's move forward then if there's no questions. Cellular respiration, you definitely don't need to write this down because we're going to have a whole chapter on it. So I'm just kind of introducing it to you right now as your textbook is doing it. Cellular respiration is the energy releasing chemical breakdown of fuel molecules. So usually when people think of respiration, they think of breathing, right? But cellular respiration is different. It does involve the intake of oxygen and output of carbon dioxide. That is true. But really, it's all about energy. And again, you definitely do not need to memorize the definition of cellular respiration because you're going to need to know how cellular respiration works inside and out. And we'll talk about that when we get there. Cellular respiration is also the storage of that energy that I was talking about being released. It's storing it in a form that a cell can use. So when you eat stuff and you break it down, you don't use all that energy, and you certainly don't use it as it's released. It has to be converted to another form. And I like that your book points out you lose about 34% of that energy to heat. Or excuse me, 34%, about 34% of it is actually converted to useful work, and the rest of it is lost as heat. So that's a lot when you think about it. That's a lot. And that's why I've got this picture of this, like a thermal picture of this person. You can see them radiating heat, right? So is there any questions about this slide? Normally, I'm not big on numbers, but if you're taking notes, I'd write that one down. About 34% of food energy is converted to useful work. And I'm not going to try to trick you. So on the multiple choice exam, your choices are not going to be like 33, 32, 34, or 36. It won't be like, it'll be largely different. So don't stress if you can't remember the exact 3, 4, 4, 4, 4, right? Don't worry about that. Try, but as long as you're in the ballpark, you should be good to go. So any questions about this slide? All right, move on. Since we were talking about chemical energy, that energy stored in the bonds of the molecules of the food you eat, that brings us naturally to food calories. And this one's really useful because, again, this is like everyday stuff. You take in calories all the time. If you're like me, you actually pay attention to the calories that you're eating, like read the label sometimes. But you definitely need to know what a calorie is. Notice that calorie has a lowercase c, but a calorie with a lowercase c is the amount of energy needed to raise 1 gram of water by 1 degree Celsius. And you need to know that number. Know that. Calorie can raise the temperature of 1 gram of water by 1 degree Celsius. So for example, if you had 100 calories, you could raise the temperature of 100 grams of water by 1 degree Celsius. Or you could raise the temperature of 1 gram of water by 100 degrees Celsius. Hopefully you can see how these numbers work. And that brings us to something called food calories. All right, you've got a bottle. So if you look at your bottle, how many calories is that per serving? Like 120 or something, 160? 240, right? So 240 calories with a drink per serving. So what does that mean? That's these calories right here. Those are food calories. That's calories with a big C. Now, a calorie with a big C is equal to 1,000 of these regular calories. So that said 240 calories. That means it's actually 240,000 of these calories, right? So you could raise the temperature of 240,000 grams of water by 1 degree Celsius with one serving of that soda, if you broke it down and released the energy. So are there any questions about the difference between a calorie and a kilocalorie, or a calorie with a big C? You definitely need to know the difference. There'll be one test question on that. I know sometimes people get a little bit anxious about that question because it will involve some math. You'll have to do some conversions, and you'll see what I mean when you take the when you do the study guide. But don't worry about it. Even if you just can't get it, just remember it's only one question. So, you should be okay. Speaking of which, that's why I put this slide right here. I'm not going to talk about it. I'm not even going to read it. But as you're studying, you can look at it yourself. So this is just a way to help you wrap your brain around all the different ways you could describe the calorie situation. And again, there's only going to be one test question. So if for some reason it doesn't get to you or stick with you, don't worry about it. So any questions so far? Here's a little picture from your book. You can see the typical calories of typical foods, and then also the typical amount of calories burnt with different activities. And again, in my opinion, that would be a really cool, not really cool, but that would be a decent independent work thing, because you could just look it up. It's like, how many calories do I burn when I play guitar for an hour? Something like that. So any questions on food calories? All right. We're actually moving really quick. So really quickly, I'm going to try to slow it down, but you guys don't have any questions. So I'm just barreling forward. Yeah, next thing. So we're done talking about the basic energy concepts, right? So there's no questions about just the basics of energy. All right. If there are not, we'll get into this next section, which is now we're really focused on energy from a cellular point of view. We're going to talk about ATP and cellular work.
When it comes to kinetic energy, and the varying on the sizes of the objects, is that I'm not really sure on exactly how much. I'm sure there's some kind of equation for that, sizes of objects. So I mean, talking like the difference between me throwing like a basketball and then shooting a bow.
Yeah.
The arrow's kinetic energy compared to me throwing a basketball and hitting the same object. Well, I'm trying to think like how would be the difference in that kind of kinetic energy?
That's a good question. And since we're ahead of schedule a little bit, I'll answer it. But for everybody listening, you just know that you don't need to know that for this class. So the energy we're talking about is very specific. We talk about that chemical energy, that potential energy stored in bonds. But to answer your question, it's actually a simple equation. So it's F equals ma, force equals mass times acceleration. So yeah, obviously the bigger something is, the more mass it has. So therefore it would have more force. And also the faster it goes, right? The acceleration.
Yeah.
So, yeah.
Okay.
Good question. And again, if you're watching this, that's nothing that you need to know for the exam. All right, so if there are no other questions, let's talk about this. The chemical energy that's released by cellular respiration is used to generate ATP. If I had to choose one sentence to sum up this whole chapter, like the most important stuff of this chapter, it would be that. Basically, I'm trying to think of all the different ways I could say it. Doesn't matter. Basically, we need ATP, right? ATP is the form of energy that our cells use. You need to know that. ATP acts like energy shuttles. They store energy obtained from food and release it as needed later. In a way, you could think of ATP as little batteries. Like, imagine everything in your cell runs on these little batteries, and that's what ATP is. So as you eat food and you digest it and then break those molecules, that's releasing energy. And that energy that's being released is not used by your cells directly. They can't use that energy. What they need is those little batteries, right? They need ATP. So you can think of cellular respiration as charging the batteries, right? So you have all these ATP that need energy. You charge them, and then that ATP just goes where it's needed in the cell. So again, if I had to summarize this whole chapter, that's what it's about. Your cells need ATP to do work. And then the next chapter, if I were to summarize it into one sentence, you could say, this is how your cells make ATP. And that's going to be respiration. But anyway, are there any questions about ATP? Don't forget anything on this slide. In my opinion, this is the most important slide. Your cells need ATP. That is the work. That is the energy. That is the form of energy that they use. All right. So obviously, since ATP is so important, let's talk about it. We're going to talk about the structure first. And like I said in chapter 1, this whole semester, we're going to keep going back to this idea of structure and function, structure and function. As far as I'm concerned, you just memorize the letters ATP. I'm fine with that. Technically, that stands for adenosine triphosphate. Then again, I don't care if you know that or not. But I guess the way that is important, even though your textbook doesn't get into it too much, is here you've got the adenosine, and then here we have these 3 phosphate groups. And what you can't tell, because you're not chemists, but I'll go ahead and let you in on a secret. Well, maybe you can. You can see that. Can you guys see that all those oxygens are negative? Hopefully you can see that, right? Those are negative. And also something that your book doesn't really tell you, and you don't necessarily need to memorize it, but oxygens themselves are very negative atoms. And also double bonds, that's also very negative. So what I'm saying here is that we have these really negative balls, and it goes back to what I was saying earlier. Things that are negative, right, they repel each other. And however much energy it takes to build something, that's how much energy will be released when you break it. And that's why the structure and function are so important to this molecule. It takes a lot of energy to squeeze that really negative ball and get it to bond with the other ones. So that's why it's important. I'm certainly not going to go into that much detail when I ask you about it on the exam, but I just wanted you to understand that's why ATP is such a powerful molecule. It took a lot of energy to build it. And then in chapter 6, we'll talk about how we built that. But for now, you just need to know that's ATP. So technically, the way your cells use the ATP is they kind of take off a phosphate group. And once that happens, that releases energy, and that's what your cells use. And I'll show you a picture of that on the next slide. But are there any questions so far? All right. Oh, sorry.
Genetically made?
What's that?
Can ATP be genetically made?
Yes. And we don't really have time to get into that. But yeah, this base right here, if you forget the phosphate part, this right here, that is one of the bases that's used in DNA, and RNA. So great question. Usually people don't notice that, and I never mention it because I don't want to get confused, because you do need to know about DNA and RNA, and that's a separate conversation than this. But yeah, that is what that is. And also, if you want to look this up for your own knowledge, I'm not going to ask you this. We teach you all this about ATP, but technically there are other similar molecules that your cells also use for energy. But to keep things simple in this 100 level class, we just focus on ATP. But if you're interested, you can look that up too for independent work. What are the other forms of energy that we use, that our cells use? All right, so like I said, the next slide I'm going to show you kind of demonstrates what I've already told you on this slide. So there you have your ATP, right? You've got the 3 Ps there. It's full of energy. And then once you lose one of those phosphates, right, that releases the energy. That energy is used for something, whatever your cell needed the energy for. And then now you have ADP. So you go from TP to DP, right? You go from 3 phosphates to 2 phosphates. And usually whatever textbook you're looking at, they usually depict it this way. When it's ATP, you usually see it looks like a sun, right? It's all jagged. And then when it's ADP, it's usually really smooth. It just indicates that the ATP has all that potential energy, that stored energy ready to be released. And the ADP, it's already released its energy. So are there any questions about this slide or the relationship between ATP and ADP? We're going to talk about it some more anyway, but if there's no questions on this, we'll move forward. Excuse me. Let's talk about that. Like I said, when you release that phosphate group, that's what releases the energy. That's what your cell's using. So we're going to talk more about that phosphate transfer. Your book points out that ATP energizes other molecules by transferring phosphate groups to them. So when we say it loses a phosphate group, that ATP, when we say it loses a phosphate group, it's not like it just goes floating out in space, right? It's actually technically being transferred to another molecule. That does some things. I don't know. Yeah, I'll talk about it. Okay. It helps cells change shape. That's why I have this picture right here. That's not in your textbook. These are little things called stomatas. There's little holes in leaves that let gases through. Sometimes they need to be closed though, because you don't want to lose water, things like that. So when these things change shape, that takes energy, right? And that closes the hole. But that's just an example. You don't need to know that. ATP also enables the transport across membranes. That one's important, and we're going to talk about that later in the chapter. And to me, I think a more important one in the context of this, not this chapter, but this whole semester, is that ATP drives the production of cells' large molecules. So when your cells build stuff, which we're going to talk a lot about later, when they build stuff, that requires energy. And where do we get that energy? ATP. So that's a really long-winded way of saying, again, like I've already said, your cells do work, and they need energy to do that. Where do they get the energy? ATP. Any questions about that? Here's some pictures from your textbook that kind of show you what I just talked about. Here's a muscle protein or motor protein. You can see that's a muscle. Where is it? There we go. So the ATP transfers a phosphate group that allows it to move. Then your muscles move. It's just an example. You don't need to know that. Same here. Sometimes, and you're going to learn a little bit about this in this chapter, sometimes it takes energy to get things into your cell. And where do we get the energy? ATP, when it transfers a phosphate group. Here we go. We're building something. We need an XY. We have an X, we have a Y, but we need an XY. It's going to take energy to build that. Where do we get the energy? ATP. And now for the easiest part of this chapter, in my opinion. This is like, and you're going to learn about all kinds of cycles in this semester, but in my opinion, this is the easiest cycle of the semester. Buckle up. Before we get to it, I like this. Your book points out that cells spend ATP continuously. So it's not like just here and there, like it's happening a lot. Plus you have to think about all the cells you have in your body. So as your body spins that ATP, right, as it's being used, we're also making new ATP. And that essentially is the ATP cycle, right? So it's recycled when that ADP is recombined with another phosphate group, and then you have ATP. It's really that easy. So here you have ATP, right? All three phosphate groups. You'll lose a phosphate group to release energy. Now you have ADP, which is not good for, it's good for nothing, so to speak. So we need to energize it again. So we put another phosphate group on it, and then boom, we have ATP. So it's that easy. You take a phosphate group off, you put a phosphate group back on. That's it. So any questions? That picture is not from your book, but this one is. How simple is that, right? You have ATP, you lose a phosphate group, and you release energy, and then you have ADP. So you use some energy to put the phosphate group back on, and the cycle continues. Are there any questions about that? All right. Like I said, we're moving really fast because you guys don't have any questions. We usually don't move this fast. So what I'm going to do, I'm going to end a little bit early today because I don't want to get too far ahead. And this will be good. You can sit back and marinate on everything I've just told you about ATP. And then later when we come back on Wednesday, depending on when we take the exam, whenever we talk about this again, then we'll start getting into enzymes and things like that. So if there are no more questions, I'm going to go ahead and X out of here.
Professor D.
Yes.
Thornabar here. Hey, so like when we eat our food, you know, like based on our diet or whatever, but when we eat our food, the ADP is like a battery, like recharging. And it just sits there. Yeah. And when we exert ourselves, like cut grass or go for a jog or a walk or something like that, that battery releases the ADP.
Right. Wait a minute. You're close. So ATP is the battery, right? That's your charged battery, so to speak, right? That's a charged battery ready to go. And then as you use it, you know, it turns into ADP, which is like a non-charged battery.
Yeah, so that's what I'm trying to say. Yeah. So
yeah. And then when
when we feel sluggish, our body is telling us we need more power. You need to charge your battery.
Yeah, yeah. To put it simply, yeah, it's a little bit more complicated than that, but that's a good way to visualize it for the sake of this chapter and for the sake of understanding ATP and ADP. Yeah.
Okay, gotcha.
Good question.
When you eat food that has more phosphates in it, is that better for the production of ATP?
That's a great question, and off the top of my head, I don't think it matters. And you can look it up for independent work. I might look it up now. I don't. There's something in chemistry called a limiting factor, and that's like, so when you're building something, you know, chemical reactions, you have your reactants and your products, right? If you're trying to build something in chemistry, the limiting factor is whichever reactant you don't have a lot of. So, for example, if you owned a pizza shop and you had like trucks and trucks of all the dough and trucks of all the cheese you need, but every day you only get one shipment of sauce. You get like one jar of sauce a day, right? So yeah, you might have a ton of cheese and a ton of whatever else you need, but your limiting factor is going to be your sauce because you only get one jar a day. So what I'm getting at is I don't think in this process that phosphate is ever a limiting factor. I don't think, but we don't even talk about that in this class. We don't talk about where that phosphate comes from, but great question. I like this. You guys are thinking outside the box. Any other questions? All right. For those of you, I'll just remind you, if I didn't say anything to you, go ahead and email me for attendance today. And then also, I guess for those of you who don't need to email me for attendance today, you still might want to email me if you want to give me your opinion on when we should take the exam, whether we take it on Wednesday or Friday. Oh yeah, also, and I forgot to mention this earlier, that's fine, this is being recorded. Regardless of when we take it, the exam will be online. So the same way you do your study guides, you go in there and like, you know, answer the questions on the study guides. It's the same exact process, except the exam is going to open up, like it'll be available to you at 8 a.m., either Wednesday or Friday, and then you'll have the 50 minutes to complete it. So pretty simple. Any questions? All right, well, I'm going to log off of this, and then I'll be back at 9 o'clock for office hours. You guys have a great day.
You too.